So is there any relation between this recharge-discharge idea and the real world? So before I go to show the results of the recharge-discharge model that we just looked at, I wanted to show these figures from a very nice paper by Chris Minan and Mike McFadden on computing the recharge-discharge, or what they call the warm water volume. So if you look at the mean distribution of the thermocline depth, which can be considered as the warm water volume, you see what we expect. You see shallower depths over here and the deeper depths on the west with some meridional scale and things like the north equatorial countercurrent, north equatorial current, etc. have their signatures, and the ITCZ, etc. in terms of the depth of the thermocline. So there is a scale, meridional scale of the accumulation of the warm water, which is real because the upwelling is bringing cold ocean water to the surface, and there is more than 100 watt per meter squared going into the ocean that is being soaked up, and then as the waters are advected westward by the south equatorial current, they are accumulating over here during La Nina and normal times, and then when El Nino happens, we talked about the processes that discharge it. So if you look at the variance, this is the standard deviation about the mean seasonal cycle of this, then you can see that there is somewhat of a higher variability in the east, which is what gives us the dynamics associated with the Bjerknes feedback and the gamma HW turn in the recharge-discharge oscillator, and the variability is somewhat less over here, but SPCZ shows its signature over here as well. Okay, and now we can go back to the idea of how the discharge happens during El Niños in the real world. So this is done by computing what is called empirical orthogonal function by Chris and Mike, and if you don't know that, you can look it up. Basically, given an array of x, y, and time, a variable like longitude, latitude, time series of the thermocline depth can be split into dominant patterns like this for EOF mode 1, which explains the most variance, and then EOF mode 2, which explains the next level of variance, and so on. Each pattern comes with this time series. When you multiply the two, you get the anomaly at any particular location. Okay, and you get a series of EOFs that add up to the total variance of the original signal. Beyond that, I won't say much, but you can see what's happening here. So the dominant mode here has this east-west pattern, which is consistent with the thermocline depth changes that we talked about. So the sign doesn't matter because you can multiply by the negative or the positive from this time series. So when it is deeper in the east, it's shallower in the west, like El Nino. If it's shallower in the east and deeper in the west, we get La Nina. Okay, multiply by the negative number. More interestingly, the second EOF has this meridional tilt. So it has got a positive loading on this side, it's called spatial loading, and a negative loading on this side. So you can see the time series. The dotted line here is the time series, or what is called principal component, associated with the meridional mode, and that actually leads by anywhere from 6 to 13 months compared to PC1, which basically says that the discharge of the warm water is happening by first the meridional tilting of the thermocline across the basin. So the entire thing is somehow shifting. Obviously could be related to the relaxation of the trade winds, but honestly this is not fully explained by anybody. And then comes the zonal mode. So the discharge is happening with the meridional mode and then the zonal mode. Okay, so this is very critical. And the recharge-discharge theory explains it this way. So you start with a depth anomaly, let's say in the discharge phase, where you have westerly anomalies, so tau e in our equations is greater than 0, so you have delta tau e greater than 0, so you have in the warm phase discharge is happened, so you have deeper anomalies in the thermocline here, so HE is positive and HW is negative with this mean level here, and after some phase the system oscillates and moves into a flat thermocline. So the Sverdrup transport has happened as shown here. You can see these SV are the Sverdrup transports that are discharging the heat from the deep tropics, and the thermocline, the temperature gradient and the thermocline gradient has gone flat, and the thermocline is shallower than the mean depth, steady state, and then you get the next phase where the wave reflections, advective feedbacks, all those things happen. Remember, this equation has the delayed oscillator built into it as well. It doesn't eliminate the waves. Okay, so you have the processes happening which begin to lift the thermocline in the east. You get the Sverdrup transport now beginning to recharge the deep tropical ocean. The eastern Pacific temperature anomaly gets negative. You get easterly wind anomalies, so you have tau e less than 0, and then you end up with a phase where again the thermocline is flat but deeper than normal, and the wind anomalies have gone to 0, and then you begin to slosh back towards this phase. Okay, so lots of details there in terms of what would self-sustain it, and if it is basically that the equatorial Pacific is an unstable system which oscillates, then you have to explain why El Niños don't occur at regular intervals. Why is the spectral peak between 2 to 7 years? Sometimes El Niños happen every 2 years, sometimes every 7 years, so those kinds of things are not very easily explained, and whether it's not even clear whether it's a stable oscillator, so that if there is a wind anomaly that kicks it, then it oscillates and then the oscillation damps away. If that's the case, then you have to understand why every kick doesn't create an El Nino. What is special about kicks that actually create an El Nino? So these are basic questions that have not really been answered yet. I will leave that here and then come to the couple of other theories in the next podcast. But I hope you understand that the recharge-discharge oscillator proposes that this recharge-discharge process can be thought of as a self-sustained oscillation, and it seems like it's a viable theory, a viable ENSO theory, because there is recharge-discharge associated with each El Nino. We don't know what the differences are between the different El Nino patterns that we looked at in terms of the East Pacific El Nino and the Central Pacific El Nino. There are already theories that show that the discharge processes are different between them, but it seems like the discharge process is involved in all flavors of El Nino, whether it's East Pacific or strong extreme El Ninos, or the West Pacific or the Central Pacific El Nino, and so on and so forth. But you get the idea that there are some fundamental intrinsic processes that occur in all El Ninos, like the waves and the delayed oscillator and the recharge-discharge, and yet many processes remain unexplained in terms of what actually triggers the onset of the discharge, and there is papers showing that the discharge onset actually happens almost 18 months before. But then, is the discharge process a necessary condition, or is it also a sufficient condition? It turns out that many times discharge happens, but El Nino doesn't grow because there is something else that is needed, maybe like this westerly wind burst or the weakening of the trade winds, and it's not clear whether they're all related or they're independent processes. So obviously still many unexplained things, but you get the idea that we know a lot and some things are still to be explained. Okay?